Hello, everyone. We from Fastcode AI are incredibly excited to present our work, ODO, Depth-Guided Diffusion for Identity-Preserving Body Reshaping at WACV 2026. Our objective is to achieve highly controllable editing, specifically making a subject fatter, thinner, or more muscular, while strictly preserving their facial identity, pose, clothing, and the background environment. Now, why does this matter? Well, the applications are expansive. In the commercial sector, it drives virtual fashion and the creation of dynamic digital avatars for entertainment. In the medical and psychological fields, it enables critical health visualization, acting as a powerful tool for patients recovering from eating disorders like anorexia or bulimia. But why is photorealistic body reshaping so exceptionally difficult? If we look at human body pose editing, we must acknowledge that fundamentally, changing a pose is a more complex geometric problem. The change in joint positions is extreme, and it requires synthesizing entirely new general pixel information to fill in occluded regions. Yet, despite this extreme difficulty, many robust methods exist for pose editing today. That is because the field has access to large-scale datasets with a massive variety of poses. These are relatively easy to create by simply extracting frames from a video of a moving person or capturing multiple photos. Reshaping datasets, however, suffer from a severe data bottleneck. We have a very limited number of samples, with very little variation in actual body shape. Because it is practically impossible to photograph the exact same person, wearing the exact same clothing, in the exact same background, but at vastly different physical weights. The examples seen on the right are from the BR5K dataset, used in a flow-based approach for body reshaping. The drawbacks of this dataset are that the body shape variation is barely noticeable, the identity is blurred out, and the dataset size is small, only 5,000 pairs of images. Because of this paired data limitation, existing methods rely heavily on 3D morphable models or simple 2D warping algorithms. These approaches have severe limitations. On the left, we see how current point-based warping tools require tedious manual intervention, forcing the user to plot out specific drag points just to get a basic edit. And on the right, you can clearly see the severe distortions that occur in both the body and the background. Notice how the warping algorithm completely breaks down when dealing with loose clothing like the striped shirt, tearing the pattern and creating highly unnatural geometry. Ultimately, these prior methods demonstrate very poor generalization to varying shapes. To solve this, we realized we had to fundamentally rethink the data. Hence, we introduced Changeling 18K, the first large-scale dataset engineered specifically for human body reshaping with consistent identity across the transforms. It contains 18,573 total pairs across 1,523 subjects. We structured this data into perfect triplets of thin, muscular, and fat variations, guaranteeing consistent face identity, clothing, pose, and background, as shown in the images on the right. We achieved this using a novel, four-stage, model-driven generation pipeline. First, identity creation. We initialize each synthetic subject with a high-resolution facial portrait generated by FluxDev. We supplemented this with license-free real-life faces from Pexels and Unsplash, yielding a robust corpus of 1,523 unique human faces. Second, identity-conditioned full-body generation. We pass these faces into Pull ID alongside standardized text prompts specifying the scene and body type to generate high-resolution images differing exclusively in body shape. Third, and most critically, background and aspect ratio normalization. Diffusion models are inherently stochastic. Even changing one word in a prompt alters the latent space trajectory, causing slight background shifts and perceived subject size differences. We designed an automated post-process to fix this. We treat the thin image as our baseline reference. We use RTDTR-V2 to detect the subject and SAM 2.1 to extract precise binary masks. We then pass the reference image to Flux Context Pro to completely remove the person and reconstruct a clean background. Finally, we uniformly scale the masks of the fat and muscular subjects to match the baseline height, compositing them perfectly onto the clean background. In the final step, we manually filtered our dataset, dropping generations with mismatched clothing, warped garments, or identity drift. This left us with 18,573 high-quality pairs for training. Given this groundbreaking dataset, we propose ODO. In our setup, the reference image is the input we want to edit, and the target image is the exact same person exhibiting the desired body shape. The core challenge in reshaping is enforcing strict spatial guidance. To solve this, we condition the model during training using target SMPL depth maps. We first fit an SMPL model to the target image, optimizing shape and pose parameters to render perfectly aligned depth maps. During training, we add random noise to the target image latents. Our main SDXL-based network, the ReshapeNet, learns to predict and remove this exact noise. This objective is optimized using the standard diffusion loss. To perfectly guide this denoising process, we inject 3 simultaneous signals into the ReshapeNet. First, the input reference image is routed through a reference net to extract fine-grained identity and clothing features, and through an IP adapter for high-level semantic embeddings. Second, the target depth map is fed into a depth control net to enforce the new geometric boundaries. Third, we provide category-specific text prompts, such as "make the person thinner," for precise semantic control. For computational efficiency, the heavy reference net and control net are kept frozen to preserve their pre-trained features and save memory. We only train the IP adapter and ReshapeNet, forcing the network to learn how to precisely fuse these signals to minimize the noise prediction loss and generate the final reshaped body. During inference on in-the-wild images, where we don't have a target depth map, we first extract the initial SMPL parameters directly from the input image. We then use Semantify, introduced by Gralnick et al., for the mapping between the semantic attributes of the human body and the SMPL beta shape parameters. By adjusting intuitive sliders for semantic attributes like weight, height, and hip size, we directly modify the beta parameters. This updates the target depth map, ensuring the generated output aligns flawlessly with the user's desired body shape. Our qualitative results on in-the-wild images showcase the ability of our model in diverse conditions. Reshaping a seated subject is notoriously difficult because the body interacts directly with the environment. But our model keeps the geometric structure of the chair and the background completely intact, even as the subject's size significantly increases or decreases. Looking at the bottom left example, our model perfectly retains the complex and highly textured design across transformations and scales the fabric pattern without introducing diffusion artifacts or breaking the visual continuity. Finally, on the right, we see subjects in dynamic walking poses, as well as wearing loose clothing. Our model understands the underlying 3D anatomy and naturally drapes the loose garments over the newly generated body shape while preserving the complex street background and depth of field perfectly. We showcase our model's precision by comparing the generated outputs directly against the ground truth and the target depth map. On the left, we have results from our standard test set, featuring highly complex, self-occluding poses, like sitting cross-legged or crouching. On the right, we showcase results evaluated on a test set generated using CDream 4.0. Our model accurately reconstructs the exact intended anatomy according to the target depth map and fits the clothing perfectly to it. Quantitatively, on an evaluation dataset constructed using our exact same generation pipeline, we establish a new state-of-the-art compared to prior flow-based methods by Ren et al. And diffusion-based methods like flux context. We achieve a dominant structural similarity of 0.77 and a PSNR of 19.07. Crucially, we drop the per-vertex geometric error down by roughly 45%. Qualitatively, for the given target weights, prior methods like the flow-based approach by Ren et al. And the diffusion-based approach, diff-body, by Okuyama et al., introduce severe distortions to the striped shirt and the subject's anatomical proportions. Our model, however, maintains flawless anatomical consistency, perfect texture fidelity of the striped t-shirt, and zero distortion. Our ablation studies validate the necessity of every component in our pipeline. If we remove the textual prompts from the conditioning phase, we observe a drop in structural accuracy and an increase in geometric error, which visually manifests as a loss of precise semantic control, particularly because SMPL depth maps cannot encode fine-grained features like muscle definition. When we remove the reference net, the perceptual error increases significantly. As seen in the visual comparison, without it, the model fails to preserve the subject's clothing texture, lighting, and background details. Since true facial likeness relies on resolving extremely fine-grained spatial features, preserving the exact identity becomes impossible without the reference net. Lastly, training our entire architecture on the smaller body reshape dataset, BR5K, introduced in the prior flow-based approach to body reshaping by Ren et al., causes the geometric error to spike and the visual generation to severely degrade. This demonstrates that our model's performance is strictly tied to the scale, diversity, and spatial alignments provided by our new Changeling 18K dataset. In summary, our key contributions are twofold. First, the Changeling 18K dataset, the first large-scale, high-resolution, identity-preserving dataset solving the paired data bottleneck. Second, Odo, an end-to-end diffusion model that achieves state-of-the-art geometric reconstruction and redefines the benchmark for photorealistic, identity-preserving human body reshaping. We hope that the public release of our dataset will help overcome the data barrier, promote future research in this domain, and inspire extensions to make human shape editing even more robust in the wild. Thank you very much for your time. I invite you to scan the QR code to visit our project website for more details.